Hey guys, again, sorry I can't be there today. Tomorrow, when I come back, we will kind of review and recap everything you guys did on Friday and everything you guys are doing today. Remember, test is this Thursday. You've got a problem set due, I believe it's tomorrow night, which is Tuesday at midnight. We can remind you guys tomorrow with that. Today, we're going to do a couple of things. But before we do that, Friday, you guys should learn about oxidation numbers with redox chemistry. Watched a couple videos. We'll do some more practice with that tomorrow. A lot of the rules that were discussed and are in your notes, we've kind of talked about that already. Group 1 and Group 2 elements, we've done that with bonding, +1 and +2 charges all the time. Oxygen is most of the time -2. A couple, unique pieces you got to remember that. We'll talk about that again some more tomorrow. So we'll review it. Hopefully you guys got most of it. Go back and rewatch those videos if you're confused. But the biggest thing is you've got to know your rules. So start memorizing those between now and Thursday. Today we're going to talk about nuclear chemistry and equilibrium. We're going to finish that up. All right. So first thing we're going to do is nuclear. This is something that on your final exam you might see one question about. Typically, the past few years, it's been dealing with decay. So these are the types of decay right here. We'll get into those in just a second. This year, I think there might be a half-life question. So those are the two big ones you could see on your final exam. So it'll be one of those two. However, it's not a big area of chemistry. There's not a ton of people in the world who use it on a day-to-day basis. So therefore, we kind of just do the basic big idea concepts with radiation, decay, and half-lives, but that's about it. It's as far as we go. So there are 4 types of decay. We've got alpha decay, we've got beta decay. All right, so we've got alpha, we've got beta, gamma, and neutron decay. Alpha, you got to know there's symbols for all of them: alpha, beta, gamma, and the neutron is just an N. Alpha is just a helium nucleus. So you've got to know that it's helium that decays, right? Decay means you're going to lose that from whatever the substance is. So when we're talking about decay, we have one element. It's nucleus. And what happens is it's going to lose part of it. So if it's alpha decay, it's going to lose a helium nucleus out of the nucleus of it overall. If it's beta, it's going to lose what we call an electron, basically, which is just electron emission. Gamma is just energy. All right, it's not really written in the equation. It's just energy. No mass is lost. All right, and then neutron, you're losing a neutron. Okay, so what this picture right here shows kind of the damage that these types of radiation are capable of. Alpha can just be stopped by your hand. Beta is higher in energy. It can go through your hand and can be stopped by aluminum. All right, gamma rays. Gamma are, we talked about those when we did electromagnetic radiation. Very, very high energy rays of energy because it is just energy. There's no mass involved. So it can go through your hand and go through aluminum. It can be stopped by lead. And then neutron decay or radiation can go through all that. It can be stopped by really thick concrete. We're talking like 3 or 4 feet worth of concrete. So you might hear or have heard before in the movies or something like that, doomsday preppers where they make a bomb shelter. Well, to make it a really good one, you need to have like 3 or 4 feet of concrete and then like 6 inches of lead inside of there as well to stop all of the radiation that could potentially be out there from a nuclear bomb. All right, so there's a lot going on, a lot of energy that's being transferred here. And so we can see that alpha's got the largest mass, so it can be stopped the easiest. The rest are higher in energy. So alpha's going to be your lowest amount of energy being radiated, whereas then beta, gamma, neutron get more and more and more energy. All right, so we're going to go into the modes of decay and writing those equations in just a minute. But let's talk about half-life as well. Half-life, you guys have maybe learned about this in math class already, but basically, as time goes on, all right, you lose 1/2 of the amount of whatever you started with. So if we're talking about particles, all right, you have 100 particles at the beginning. After one half-life, you're going to be cut that number in half, so down to 50. After 2 half-lives, you're going to cut it down by another half, so you had half of a half, which is a quarter. So you're dividing by 2 basically every single time. So if we started with 100 over here, then we'd go down to 50, then we'd go down to 25, 12.5, 6.25, and so on and so on and so on through all the half-lives. Excuse me. Now, in theory, okay, you can never really lose every piece, right? Every particle that you have. In theory, there's always going to be something left. Okay. Now, we're not going to deal with 5, 6, 7, 8, 9 half-lives. Typically, if you're asked a problem, it'll be 1 half-life or 2 half-lives. And the other piece that we could see is, all right, well, if I undergo 2 half-lives or this, how long would it be? So those are the types of problems that we're going to see. All right, and that's really all that we're going to do with nuclear chemistry, is learning about these types and writing their equations, which we're about to get into, and then dealing with half-lives. Okay, so flip to the next page in your notes. All right, these are the nuclear equations. So the big idea to remember is that it must be balanced on both sides by mass and atomic number. Okay, so the math doesn't lie. All right, the rest will take care of itself. Excuse me. So these examples we're going to work here together. Alpha decay. So first thing, decay means that we're going to lose it. So it's going to be on the right-hand side, the product side of our reaction that we're going to write, you're going to have an alpha particle. Okay, which, if we remember, if we flip back to the previous page, an alpha particle is just a helium nucleus. So that's what we're going to show it as. Okay, so we're going to start with our nucleus that we are given. All right, so that's iridium 193. IR, we've got 193 up top. We've got atomic number of 77. All right, and then we're going to draw our arrow. We know, since it's alpha decay, all right, we're going to have an alpha particle, so that's the first place we want to start. So that's a helium atom with a 4 up top and a 2 for the atomic number. So it's 2 protons and a mass of 4. So decay, again, means that we're going to lose it. All right, that means we're subtracting this. So the piece that we're missing, excuse me, is the new nucleus, what it decayed down into, what it broke down into. All right, so it's undergoing this alpha decay radiation to produce a new nucleus. So what we're going to do is that, again, both sides must be balanced. So the arrow is kind of really like an equal sign. Our number on top, or all the tops, have to add up on both sides, and our numbers on the bottom have to add up on both sides. All right, so the new piece that we're going to figure out is, all right, 77. So we have 2 already, so you can think about it like 77 minus 2 is going to be what? Well, that's 75. Or you can think about 2 plus what equals 77. Same thing, whether you're subtracting or adding it in there. So 75 is going to be our new atomic number. On the top, we're going to take 193 minus 4. All right, so that's going to be 189. Now we've got to go ahead and figure out what is that symbol that goes along with it. All right. All right, so get your periodic tables out if you don't have them already. Excuse me, we've got to figure out now what our new symbol is going to be. And if you think about it, you guys should know this. What are we going to look at? What's going to guide us to figure out what our new symbol is? You're right, that's going to be our atomic number. Okay, so 75 now is going to guide us. Excuse me, look at our periodic table. All right, if we look for number 75, we'll zoom in right here. So we were iridium at first. Now we're going to be rhenium. All right, right here. That's our new symbol that we're going to have. So this goes from iridium 193 isotope, and it's going to go through alpha decay, and now it's going to be rhenium, Re, rhenium 189. All right, so that is, again, alpha decay. We lose an alpha particle. All right, it's that simple. Don't make it harder than it needs to be. Let's take a look at number 2 here. All right, number 2. So now we have beta decay. So if you don't remember what beta decay is, let's go back and take a look. Beta decay is electron emission. So this is the particle that we're going to lose. The same process is going to hold true. Okay, so we've got down what we have. We've got cesium 133. All right, so atomic number is 55. It's going to undergo beta decay. So we're going to draw our arrow. It's going to lose an electron. Again, if you don't remember, go back and take a look. We've got a 0 on top and a -1 on the bottom. Okay, -1, All right, plus what? So now we're going to do the same thing. We're going to subtract out those. Well, if we take 133 minus 0, what do we have? It's still going to be 133. So our mass number on top hasn't changed. Now, 55 minus a negative 1, what's that going to really do? If you minus a negative 1, all right, so plus both of those. Oops, plus. Okay, so we're going to have 56. Go back to your periodic table. We're going to find number 56. Zoom out. Okay, over here. That's going to be barium. Okay, so now barium is our new atomic symbol. It is that easy. Now I know I put a plus sign here, but if we take this back, now take a look. The right-hand side is going to equal the left-hand side. Okay, we didn't do that up here, but same thing. If we take this and add these together right there, 4 plus 189 equals 193. 2 plus 75 is 77. Here, 56 minus 1, or if we add a negative 1 to it, is 55, 133, 133. It is that simple with nuclear decay. That's all we have to do. Number 3, I want you guys to, well, I want sub to pause the video for a second, and then you guys try the formation of polonium-210 by alpha decay. All right, so hopefully you guys tried that. Start with what you're given. Now it says formation. Okay, formation. Now that means that polonium-210 is going to be in your product side. Okay, because you're forming that. So PO210. Again, this is hyphen notation. It's good that we're doing this now because our final exam is coming up in a couple weeks. All right, couple weeks. We don't have much time left. Okay, so hyphen notation. It tells you the mass number. Mass number goes at the top. If we want to find our bottom number, go find polonium on the periodic table. All right, so if we scan over to here, polonium is, excuse me, sorry, that went really weird. Polonium is 84, so that's going to be our bottom number. All right, so 84. So that's our target. We're trying to form polonium-210. Well, we know that we're using alpha decay, so alpha is a helium particle, helium nucleus. It's got a 4 at top, it's got a 2 right here. So now we're working backwards. Now we're going to work backwards. What plus 4 equals 210? Or 210 minus 4 is going to be 206 is our new mass. And then what plus 2 is 84? Well, that's going to be 82. So again, go to the periodic table, figure out what 82 is. That's going to be lead, which is right here. And there we go. You have a built-in check. This side should equal this side. So 206 plus 4 is 210. They balance out. 82 plus 2 is 84. They balance out as well. All right, so nuclear decay is that easy. Whether you're forming it, forming just means that's your product. And if it's undergoing decay, that's what you're starting with, and it's breaking down into the other pieces. All right, if you have questions, we can review it tomorrow, all right, when I get back. The other type of nuclear piece that you're going to have to look at, all right, are half-life calculations. And as I said before, maybe you guys have seen this in math class, maybe you haven't. All right, now there's different equations that you can use to solve it. All right, I personally just like to reason out. Okay, so what is a half-life? Well, a half-life is the time required for half the atoms of a radioactive nuclide to decay. All right, radioactive dating, all right, uses the knowledge of half-lives. Carbon-14, I'm sure you guys have heard about before in history class. It can give you the approximate age of an object, all right, to figure out, different organic material or different other inorganic material as well. So you can set up a ratio, all right? It says 1 half-life over the time of the half-life equals the number of half-lives over the given amount. That works, all right? Or you can just kind of reason it out. And that's really typically the way that I approach it, is I like to think, okay, this many half-lives, this is how long those half-lives are, and I can just do the math from there. All right, so we're just going to jump right in. All right, it'll click at a different time for every student. All right, it's no big deal, but work it out. Like I said, if you have questions, tomorrow we can review it together. So here we go. Let's jump into this example problem right here. It says phosphorus-32 has a half-life of 14.3 days. How many grams of phosphorus-32 remain after 57.2 days if you start with 4 grams of the isotope? So to be honest, it doesn't really matter, this part right here. that it's phosphorus 32, it's just telling us that basically it's a radioactive material that's going to break down. We know that 1 half-life equals 14.3 days. We have a total of 57.2 days. So the first thing I want to do before I figure out how much is going to be left over from my original 4 grams is I need to figure out how many half-lives have I undergone. So to do that, I'm going to take the total number of days, so that's 57.2. I'm going to divide it by 14.3. All right, I'm going to go to my calculator really quick. Sorry for the change in scene here. So 57.2 divided by 14.3. I hit enter. That's 4. Okay, so let me go back. Excuse me. So when I do the math here, I get 4 half-lives that have occurred in 57.2 days. All right, 4 half-lives have been undergone. So now what I'm going to do is I'm just going to start dividing that number by 2 until I do that 4 total times. Now you can do it like this. You can take 4, you can do it over, well, let's see, half raised to that power. All right, so that's going to be, 2 times 2 is 4, times 2 is 8, times 2 is 16. So 4 divided by 16 is really kind of what you're doing. Or, if that's too much for you, just start dividing by 2. So this is going to give you 2 grams. All right, divide by 2 again. This is 1 half-life here. This is your second one. So that's going to be 1.0. Divide by 2. This is your third half-life. All right. That's going to be 0.5. Okay. And divide by 2 again. And my final answer is going to be 0.25 grams. So whether you do it like this, where I kind of mapped it out, divide by 2, divide by 2, divide by 2, okay, or you do it like I said at the beginning, 2 raised to whatever power of half-lives you have. So this is going to equal 4 divided by 16. Same thing, you get to the same answer. Either way that you can reason it out, go for it. All right, don't overcomplicate this nuclear stuff, folks. Okay, it is that easy. Let's do another problem here. Okay, I want you guys to try this try problem. So, sub, please pause the video at this time. Give them a couple minutes to work it out. All right, so you guys should have tried this on your own. Half-life of cobalt 60 is 10.47 minutes. How many grams will remain after we have 104.7 minutes if you start with 10 grams? So yeah, I give you the answer, folks, but you still got to work it out because you may have to do this on your final exam. All right, so we're going to take it 104.7 divided by 10.47. The math should be easy here, folks. That's going to be 10 half-lives. Okay. Now you can start dividing by 2, dividing by 2, dividing by 2, or you can do it like I said the other way, 10.0 divided by 2 raised to the 10th power. Okay, so that's going to be 2. All right, let me go to my calculator really quickly. So it's going to be 2, let me see, raised to the 10th. All right, so that's 1,024. So if we take 10 divided by 1,024, we should get that answer that we see, 0.00977. All right, if we go back to our thing here, 1,024, 0.00977 grams. Exactly like that. Okay. Now again, if you wanted to write it out and do it the long way, 10 divided by 2 equals this over 2, and just keep doing it, go for it. All right. I don't think that the state would give you something that's this big, that many half-lives, but they could. So you've got the shortcut way where you just raise 2 on the bottom to whatever power of half-lives, and you get your answer. Again, if you're confused, if I'm going too fast for you, one, this video is already posted to YouTube, so you can go back and rewatch it, or ask me questions tomorrow. Okay? Now that's one type where you have to figure out how many grams will remain. The other type is then figuring out what is the half-life. Okay? So if we have a 100-gram sample here, decays to 25 grams after this many days, all right, then we can do back calculate. So the way that I do this is I just take my original amount. Again, there's different ways you can solve it. So if you know of a different way or figure out a different way that works, go for it. Try it. Me, I like to just rationalize it. So I'm just going to take my original amount. I'm going to divide by 2 until I get to how much was left at the end of the decay. So 100 divided by 2, that's 1 half-life. That's going to give me 50. So I'm going to jot a 1 down there. Then I'm going to do 50 divided by 2 equals 25. All right, there's my second half-life. Oh, look, there's how much it was. So how many half-lives did I have here? 1, 2. So if I had 7.648 days for 2 half-lives, how many days will it be for 1? Well, I'm just going to take my total number of time, and I'm going to divide it by the number of half-lives, which in this case is 2, and I should get 3.824 days, just like the answer says. Okay, so we've got some practice here. Don't go and start working this just yet. I'm not saying this is homework. Okay, we're going to pause, but those are the 2 types of problems that you could see with half-lives. Now we're going to go back and we're going to review some equilibrium and talk about Le Chatelier's principle. All right, so sorry, I'm going through all the notes. I will tell you guys at the end of class or at the end of this video what your homework is, so don't just start doing it because you may not have to. All right, so if you remember back to last week, it would have been last Thursday, we started talking about equilibrium expressions, right? K equals the concentration of your products over your reactants. Okay. Same thing holds true. One thing we didn't talk about were acids, bases, and salts, right? Nothing's really different here, folks. It's just saying that Ka is the ionization constant or the dissociation constant for your acid. Kb, same thing. It's just talking about your base. It's the hydrolysis constant. Okay, it's still the same thing. Remember, somebody in one of my classes, I forget who it was, asked me, well, why do you have all these different subscripts? Well, they tell you slightly different things. Okay, so if it's Ka, it's talking about an acid. If it's Kb, it's talking about a base. If it's Kw, we already talked about that. You guys should know that Kw, right, equals, well, it's 1 times 10 to the negative 14 value, right? We did that when we did our conversions between pH and pOH. Okay, but it's still the same idea. How we got that is it's Kw of our products over our reactants. But if we take a look here, in all of these examples, okay, and we're asked to write the equilibrium expression, okay, it's the same way as we did last week for the KEQ, right? Products over reactants. But what's the big thing you got to remember? What does it only affect? Well, it's only affected by, right here, it only includes gases and aqueous solutions. Liquids and solids have no concentration, so we will cross them out. So first thing I'm going to do is I'm going to say, okay, here's my example. I'm looking for only aqueous and gases. Liquids and solids don't matter. So water, I'm going to cancel that out. It's not going to have any impact. So if I'm writing the Ka for this sort of dissociation of this acid base, weak acid ionizing, breaking down partially of acetic acid, all right, it's still my concentration of my products over my reactants. So what products do I have? I've got H3O plus times acetate, and then it's all over my acetic acid. Just like that. All right, so even though the K looks a little bit different, it's still the same process. So Kb, same thing, cross out this water. It's not going to have an impact. All right, so it's my products. It's going to be ammonium ion times the hydroxide ion all over ammonia. Oops, sorry, it's not gas here. And same thing down here. Water's not going to play a part. This is why with Kw, we could say that, oh, it's the hydroxide ion concentration times the hydrogen concentration, because that water was a liquid here as our reactant had no impact on it. That's how we get Kw. So there's a little review when we did our acids and bases a few weeks ago. All right, so why again? Why is this important? Well, a system at equilibrium wants to stay at equilibrium. It'll shift to adjust the changes, to adjust to any changes for it to stay at equilibrium. Now, before we get into this, I'm going to have you guys watch a video. So I'm going to pull it up right here, and you guys are going to go ahead and watch this right now. This too is in my playlist for this unit. So go ahead and watch this while, all right, then we'll go back and talk about it a little bit more.
In this lesson, you will learn about the Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is the Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary, Le Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium.
All right, so let's go back to our notes and let's talk about it. Now, I know that this is going to be probably the most confusing piece. There's going to be the most questions on when I get back tomorrow, and that's okay. This is something that will click for each person at a different time, like things have all year long. So just keep that in mind. Now you've got to know these 3 conditions here. And I know the video said about temperature. Well, we'll talk about temperature here a little bit later. Okay, so excuse me, don't worry about that. Concentration. So like I said, if you increase on one side of the reaction, you're going to move away. So we're just telling where's it going to shift, to the left or to the right. All right, so again, if you increase it like it showed with there, you want to move away, again, trying to balance out that teeter-totter. Basically, you want to move away to the side where there's less, all right, of a concentration added. So you're going to consume the excess, producing more of the other side, which will then balance it out like a teeter-totter. So I highly recommend that as we go through this, if you're struggling with this today in class, especially if I'm not there, go back and re-watch that video that I just showed you. It is in the Unit 15 playlist on my website, or on my YouTube channel. Okay, so go and take a look at it. If you decrease the concentration, you're going to move toward the decrease because you want to replace what you were taking out. Pressure again, only for gases. It's only for gases. All right, and you're looking at the number of moles. All right, so kind of like we talked about last week when we were looking at the K expressions. All right, we counted up the number of moles. Same thing. Increase, you're going to go to where there's less gas moles. Decrease, you're going to go to where there's more gas moles. All right, and the temperature depends on if it's exo or endothermic. All right, exo or endothermic. All right, and then temperature, like I said, we'll get into in just a few minutes. So here we go. Let's look at some examples. Like I said, for excuse me, each person it may click at a different time. We're just predicting the shift. Is it going to go to the right or is it going to go to the left? So in letter A, we're going to add phosphorus pentachloride. So that right here is on the left of our reaction. So if we're going to add it, that means this is going up, which means it's going to get heavier. We're changing the concentration. Okay, it doesn't say anything about gases, doesn't say anything about pressure here. If it's saying adding 1, we're changing the concentration. So we're increasing the concentration on the left side. That means if we're thinking about a teeter-totter or a seesaw, it's like this now. All right, where it was balanced before, now it's not. Well, where's it got to shift to balance that out? It's going to have to shift this way to balance it out. So now it goes from being lopsided back to this way. All right, that's the idea here. So if we add PCl5, we're going to shift to the right. We want to go away from that. So we produce more of our products. All right. Now, obviously, if we're going to add it and it's going to shift right, if we remove PCl5, that means this is going to go down. So think about it like your teeter-totter again. We're removing something on the left. That means the right side is going to get heavier. And now our seesaw looks like this. Well, we need to move it back this way to get more sort of quote-unquote mass, but it's really concentration, to the left to then balance it out so that it's even again. All right, so we're going to go shift to the left, all right, if we remove it. Now, letter C is increasing the pressure. Well, what do we look at with pressure? Pressure, we look at the number of moles. So on the left-hand side, we have 1 mole. On the right-hand side, we have 2 moles of gases. So an increase of pressure means we're going to shift to where there's less moles of a gas. Where are there left moles? To the left. Okay. Now, those ones we talked about already, and that was in that video. Let's skip over D because that was with temperature. We'll watch another one here in just a second. All right, E, concentration. We're adding one of the substances. All right, so let me get rid of the moles here. We're adding Cl2. What's that going to do to our seesaw? Well, it's going to make the right-hand side go down, which where do we have to shift then to balance it out? We have to shift to the left, away from that addition. Okay. All right, let's talk about temperature. Let's go watch a quick video again to talk about temperature.
In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. Le Chatelier's principle states that a chemical system at equilibrium always works to restore equilibrium when it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction where reactant A reacts with reactant B to produce product C and product D with a change in heat of minus 75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress. Decreasing the temperature would cause the system to produce more energy, therefore the exothermic reaction would be favored. The dimerization of nitrogen dioxide to...
We're not going to worry about that. You guys go watch the rest of the video. It shows an example. I don't want to show it and then confuse some of you. So let's just jump back into this example here. So basically, every reaction that you're given, and you have to figure out, what's going on with the shift with Le Chatelier's, they're going to tell you if it's exothermic or endothermic. Okay? Exothermic, right, means you are releasing energy. You're releasing heat. Okay? Endothermic means you are absorbing it. You're taking it in. Right? So, when you look at this reaction here, it says that it's exothermic. That means that the forward reaction is exothermic. As you go from left to right, you are releasing heat. So, it's getting hotter. All right? Well, if it's getting hotter as you go from left to right, all right, if you were to increase the temperature on the system, it wants to go back to the left where you would cool it back down because it's getting too hot. All right, so it's doing the opposite of whatever you see here. If you increase temperature and it's an exothermic reaction, it's going to shift back to the left, all right, because it wants to go away from where that heat is. If you decrease the temperature, it's going to do the opposite. It's going to go toward the exothermic. Okay, it's going to go toward the exothermic. Now, if it was the opposite, if it was endothermic, it would be flipped around. Increase in temperature, you're going to move away from endothermic, all right. And you're going to move toward the endothermic if you increase the temperature, and if you decrease it, you're going to move away from it. Okay. Again, that's very confusing. I can explain it more tomorrow, but let's take a look here. So we'll take it one example at a time. This is an exothermic reaction, meaning heat is going to be produced. As you go from left to right, there's a lot of heat over here on the right-hand side. So we're going to say plus heat as one of our products. Okay, is one of our products. Now, we're going to decrease the temperature. That means we're going to decrease the right-hand side. Okay, so it's like this. Where's it got to shift to get it back to be balanced? Well, I'm sorry, I drew it wrong. All right, if we're decreasing it, that means it's going to go up like this. It's going to shift to the right. All right, so it's like taking it away. Heat, we're going to treat it like a product or like a reactant. All right, so this right here, decreasing the temperature, we're going to shift it to the right. Now, I know I may have just confused some of you. I want you guys to try your best. All right, try your best right here with the you-try problem. So please pause the video at this time. Give them 3 or 4 minutes to try their best with this, and then I'll come back and explain it. All right, so let's take a look here. Okay, adding carbon dioxide. Is carbon dioxide a product or a reactant? All right, carbon dioxide is over here. So we're going to make this go up. Think about it in terms of a seesaw. If you increase sort of the weight, if you add another person to one side, it's going to make that side go down. All right, so we're increasing it. Well, to shift, to get that to balance out, it's got to go back this way. So adding carbon dioxide, we're going to move away from where we added it. We're going to shift back to the left to make it go back to equilibrium. Letter B, we're going to remove oxygen. Okay, remove oxygen. That means this is going to go down. All right, so we're taking that away, making it quote-unquote lighter in terms of the seesaw analogy. Well, that means the right-hand side is going to be heavier. Where is it going to shift to go back to being equal? It's going to shift to the left, just like that. Now, pressure. Again, we're going to look at the number of moles. So count up your number of moles. We've got 2 right here, and we've got 1, so we've got 3 on the left, and we have 2 total on the right. Well, let's go up here. A decrease in pressure means we're going to shift to the side where there's more moles of gases. So that means where's the more? When we decrease, that's on the left. We're going to shift left here. Letter D. Here's that temperature piece. Notice how this one is written. Okay, is this exo or endothermic? Well, it doesn't tell us in terms of words, but exothermic means that you produce energy. So it's going to be on the product side. If it were endothermic, we could cross that out. It would say plus 167 over there. That's how we know it's endothermic, because it's on the reactant side. Well, it's a product here. So think about it in terms of another substance. Okay? If we're going to decrease the temperature, that means we're going to make this amount go down. Decrease that. So if we think about our seesaw, that means this is going to go like this. Okay? The right-hand side is going to get lighter, and so our seesaw is going to be unbalanced. So where's it got to shift to make it go back to equilibrium? It's going to shift toward that energy because we removed it. We made it lower. Okay? So think about temperature or that heat in terms of another reactant, and it's just like the same thing as concentration. All right? Exothermic just means that your energy value is on the right. Endothermic would be over here on the left. All right, again, if you're confused with it, we can talk more about it tomorrow. So what I want you guys to do now with the rest of class, your homework tonight is to try your best, all right, with, let's see, I want you guys to try your best with the top one, just the top box on page 5 in your packet, and I want you guys to go all the way back here with nuclear. And I want you guys to do your best with these 6 problems right here. So you've got the rest of class to work on 1 through 6 on page 10 in your packet. And then the top set of boxes, the top chart on page 5. All right. Like I said, tomorrow I'll be back. Hope you guys have a great day. If you have questions, save them for me tomorrow.